So hi everyone, welcome back to a new edition of Seminario de Probabilidades de Chile. Today we have the pleasure of having Pablo López Rivera from Université Cité, who's going to talk to us about on Wu's inequality and the Poisson-Föllmer process. All yours, Pablo.
Thank you so much for the invitation. First of all, it's quite a pleasure to be here. Well, in this Zoom invitation, but thank you so much. I feel home. Okay, so I'll start. The title doesn't say that much, so I'll motivate it with first giving the context of what is a functional inequality, and in particular, what are the functional inequalities which hold on discrete settings. Okay, so first of all, we begin with the classical Gaussian measure, which is a nice object in terms of functional inequalities. First of all, we have that it satisfies Poisson-Föllmer inequality. That is, it says that for each smooth function, we have that we may bound its variance with respect to the Gaussian measure, with respect to this energy term, which is just the expected value with respect to the Gaussian measure of the square norm of the gradient of f. Okay. And then we have a stronger inequality, which is the Gaussian log-Sobolev inequality, which says that for each, again, as a smooth function, we may control the entropy of f squared with respect to the Gaussian measure. That is bounded by a constant, which is 2 times this energy term, which is again the same thing. And the entropy, here we have the entropy. This is the classical Shannon entropy, relative entropy with respect to the Gaussian measure. Okay. So then I wanna convince you why it is important to have some functional inequalities. So first of all, in terms of concentration, this is quite important because, for example, if we have a measure which satisfies a Poisson-Föllmer inequality, then we have that this any random variable which is distributed as this measure, then it has two exponential tails, which is kind of important. And for example, if we have a measure which satisfies a log-Sobolev inequality, then it satisfies sub-Gaussian concentration. And this is quite important as well for applications, for example, in statistical physics models, in machine learning, etc. Okay. And on the other hand, we have that functional inequalities are quite important in order to control what is the long time behavior for microprocessors. So for this, in particular, I want to be really precise. I want to motivate this application. So I'll do it here in the board. So we'll suppose that we have a Markov process. Suppose that it is a quite nice Markov process. Let's say that it is a diffusion process. Okay. So then we may define we may take for any bounded function or unmeasurable, we may define its semigroup PT, that is, we represent the time t, acting on this function at the point x, defined as the expectation, as when the process is starting from the point x of f of xt. Okay, so this object in particular quantifies or represents in some sense the law of the process xt. Okay, additionally, suppose the following. Suppose that there exists a measure, probability measure, such that we have that if the process, the initial law of the process is distributed as this law, then for each time, the process is gonna have the same law. Okay, so we're supposing that we have an invariant measure. Okay, additionally, suppose that this invariant measure is ergodic. That is, for each function f, we have that the law of the process acting on the semigroup, or in terms of the semigroup, this converges as the time goes to infinity to the expectation of with respect to the measure mu of the function f. So this is ergodicity. The thing is that if we suppose that we have this hypothesis of ergodicity, this doesn't say anything about the rate of convergence. Okay, So actually, we have a nice result that tells us that our stated proposition, if mu satisfies a Poincaré inequality, then we may quantify this convergence as the following. We have that the variance with respect to the measure mu of PTS is bounded by exponential of minus a constant times the time, okay, times the variance with respect to the measure mu of F. So then, if we have a Poincaré inequality, then we have exponentially fast convergence toward the equilibrium, which is quite useful and quite nice in lots of settings. Let's say mean field games, diffusion processes, etc. Okay, so I hope that I convinced you that having a functional inequality is not just an esoteric thing. It's something quite useful. Okay, so we'll talk in particular in this talk about the Poisson distribution. So we recall its classical definition. It's a measure on the natural numbers, such that it has this really concrete distribution. Okay, and in some sense, it's a nice analog of the Gaussian measure for the discrete settings. Okay, for example, we have some kind of TCL. Okay, so actually the question that we will try to answer is what happens for this measure in terms of functional inequalities. Okay, so first of all, recall what was the Poincaré inequality for the Gaussian measure. It was this kind of inequality. If we want to extend it towards the Poisson measure, first of all, we may see that there is an obstruction. Of course, in discrete settings, we don't have any notion of gradient. Okay, so that's a problem, but it's not a big problem because indeed we may define this finite differences operator df as just this. Okay, so then we may use this definition as a gradient. Okay, so actually for Poincaré inequality, we have it. And it has the following form for each function. We have that its variance with respect to the Poisson measure is bounded by a constant, which is t. T is the parameter of the Poisson distribution, times this energy term. Okay, the expectation with respect to the Poisson measure of the square norm of this finite differences operator. Okay. Then what happens for the log-Sobolev inequality? Recall the Gaussian log-Sobolev inequality in the form which was proven by Gross. Okay. So we wonder what happens for the Poisson measure. The thing is that unfortunately this kind of inequality cannot hold. Why? Because, for example, suppose for a second that this inequality is true. Okay, so suppose that we have there exists a constant c such that we have this inequality. So then, in particular, for this very particular function f, which is the indicator of the tail. Okay, we are making we vary it with a parameter k. Okay, we have first of all we may compute the left-hand side of the inequality, the entropy. So then, of course, we have that f squared is the same as f because this is an integer function, and then we have we may compute its entropy by definition. Okay, the thing is that this function here is always zero. For example, if f takes the value 0, of course this is 0. But then if f is equal to 1, then log of 1 is just 0, so this is equal always to 0. So then we have that this entropy is just this quantity here. Okay. And then we have that expectation of an indicator function is just the measure of that set. So we have that entropy has this value. And on the other hand, we may compute the energy term, and we have this. And then the thing is that, okay, if we apply the inequality, we get this inequality, which is impossible, because if we take k large enough, we have that this term here goes to 0 quite fast, but on the other hand, this term does not. Okay, so actually having having a log-Sobolev inequality is not possible for the Poisson measure. Okay, if you want to have a more simpler or direct argument, you may say, okay, Poisson measure does not satisfy a sub-Gaussian concentration, then we cannot have a log-Sobolev inequality. Okay, so that's a problem. But we
Just
have
one question, Pablo. I got lost
yes.
in that part. So
Yes.
before, why the left side is also going to 0, no? So it's like x log x.
Yeah, but not that fast. That's the thing.
Okay, it's just the speed. Yeah.
Yeah, that is the speed. Yeah. Yes, that's the thing. That's the thing. Yeah.
Okay.
So then we have that our inequality is not possible, but we have an alternative. In the Euclidean setting, because of the chain rule, we have that the Gaussian log-Sobolev inequality is actually equivalent to this L1 version. Here, observe that we replaced f squared by just f, and we have this different energy term. This just follows to apply the function square root to the former gross log-Sobolev inequality. Okay. So the thing is that in the discrete setting, this finite differences operator does not satisfy the chain rule. So actually, we have that this inequality here in its discrete version is no more equivalent to the former gross log-Sobolev inequality. So actually, we may hope that this could be possible for the Poisson measure. And indeed, it is the case. We have, this is a theorem by Bobkov and Ledoux. They prove that actually this inequality holds, that for each positive function, we may control its entropy with respect to the Poisson measure by a constant which is T, the parameter of the Poisson distribution, times this energy term. Okay, so this is what we call a modified log-Sobolev inequality. Okay, the thing is that after 2 years after, we have an improvement by Wu. Okay, we have that actually the inequality by Bobkov and Ledoux could be improved. We have that he proved for the Poisson measure the following the modified log-Sobolev inequality. The only difference here is that the energy term is gonna take this form here using this function psi, okay, which has this form here. Okay, so the thing is that first of all, this is an improvement of Bobkov and Ledoux because of this inequality here. Okay, this energy term, the Wu term, is always lower or equal than the Bobkov and Ledoux term. Okay. If you want to have a more concrete expression for this energy term, you may do the computation and you get actually this expression. Okay, so this is a more concrete workable expression. So then, what are the objectives of this talk? First of all, we want to give a new short stochastic proof of Wu's inequality for the Poisson measure based on an entropy minimizing process, which we call the Poisson-Föllmer process. Okay. Secondly, we want to use this process as well to obtain some stability results for Wu's inequality. I am going to introduce all these notions, that is the Poisson-Föllmer and stability at its moment. Okay. And finally, we want to extend Wu's inequality for log-concave perturbations of the Poisson measure. Okay, again using the Poisson-Föllmer process and some Malliavin calculus on the Poisson space. Okay, are there any questions up to this point?
Yeah, another question. So how tight is this inequality?
How tight?
Yes.
This is actually like let me go back, the best inequality that we can have in terms of modified log-Sobolev inequality. It is sharp. Okay. For example, if we take functions of the form f equal to exponential of a k plus b, where k is the variable, then we have that this is tight. Yeah.
But in those cases, aren't the two upper bounds equal or not?
Yeah. In that case, we have the equality. Yeah.
Yeah, so well, I don't know exactly what is the good question, but somehow you cannot find a function. Yeah, okay, so there could maybe a better function phi, but or no?
Yeah.
Like in this sense that he finds this a little bit better.
Yeah.
Okay.
Yeah, he found this, but actually it's been like 24 years without having any better thing. And the thing is that actually this psi term is quite natural. It appears, for example, in satisfies phi entropies. It's quite natural in some sense. We will see that it's something what is expected. In fact, you can see it from the proof of Wu. Okay.
Thank you.
You're welcome. So, are there any questions before starting with the content of the talk? If not, then I will continue. So first of all, we will begin with this short proof of Wu's inequality, but we need a lot of machinery to do this. So first of all, we recall what is a Poisson point process. So we start with a metric space, with a metric space E, okay, given with a metric, and we put a sigma finite measure on it, nu, and we have, of course, the Borel sigma algebra on it. So then we may construct the classical, the canonical Poisson space related to this metric space E as the following probability space. Omega, we take it as the following. We are taking all these measures, these point measures. Here n could be infinity, and we have that these points xi are going to lie onto the space E. Okay, so are these kind of measures. The sigma algebra is the one that makes all these applications, all these maps measurable. Okay, and what is the measure that we're going to put, on this space? We define the measure P. Okay, Pascal P as the following. First of all, we have on this space we have of course the canonical process, which is just the identity function. So then we say that that P is a unique law constructed on this space such that for each Borel set B, we have that the measure of the measuring this set using the canonical process, that random variable, that's a random variable that has law Poisson proportional to the measure of the Borel set B. Okay, considering the measure that we gave at the very beginning on the metric space. And on the other hand, we're going to suppose that for each disjoint collection of Borel sets, we have that these random variables are actually independent for this measure. Okay, so this is the classical Poisson point process. Okay. So then the thing is that we may look at a very particular case, which is the following metric space. We are going to take E as the interval 0t times the non-negative numbers. Why we are putting this interval 0t? It's because we want to do some stochastic calculus on this space. So we need some notion of time. Okay. And we put as the measure nu, we just put the Lübeck measure. Okay. And then we consider omega fp as the associated Poisson space to this metric space. So then consider the canonical point process. And as I said before, we actually wanna do some stochastic calculus, so we need a filtration. So we may define ft as the following. This is gonna be this filtration here. We're gonna make at time t measurable everything, considering the restriction of until time t, which is quite natural. Okay. The thing is that we may consider, let's say that we have some process lambda indexed by this time, which is going to be defined on this probability space, and we're going to suppose that it is predictable with respect to the filtration ft and bounded. Okay. So then what we can do is that we can actually define the associated counting process to this stochastic intensity lambda, we'll say, as the following. For each instant of time, okay, what we're going to say is that x lambda at the time t is going to take the canonical process, that is a measure, and we are going to count how many atoms we have below the curve of lambda s up to time t. Let me draw a little bit how does this look. So the thing is that here we're going to start with our metric space, which is just the interval 0t times the non-negative numbers. So here we have the instant t. And then the thing is that if we look at a particular path, let's say omega is just going to be a sum of atoms, okay? So then we may say that this is going to look that I am going to sample some atoms on this space. So this is going to look like this. Let's say that we have these atoms here, okay, lying in this space. And therefore, this particular omega, what we have is that we have, let's say that we have an stochastic intensity process lambda t, okay? So then this looks like this, let's say. So this is lambda of omega. Well, of course, the collection of red points is omega in this case. And the thing is that, for example, say for the instant s here, okay? Here we're gonna compute what is xs of lambda at omega, at this very particular omega. So what do? We count how many atoms we have below the curve. So in this case, we have 1 and 2. So then we have that this is just gonna be 2, okay? And for example, another example, if we wanna compute x big T, lambda of omega, then we do the same, we do here this time T. So then we count every single atom which lies below the curve. So this sum up to 3. Okay. So this is more or less what is a counting process associated to an stochastic intensity. Are there any questions about the model, the process? No? Okay, cool. Then we'll continue. The thing is that we have quite nice connections with we have actually some nice representation formulas for these kind of processes. This is reminiscent from the Bouy-Dupuy formula for the Brownian motion. So then what does this formula say? That if we take f bounded and measurable function, and we take the Poisson process, the Poisson measure as a reference measure, then we may compute this function, which is the log, let's call it the log moment function related to f, okay? We have a nice variational formula which says that this is actually equal to this supremum. We were taking the supremum amongst the class of all the non-negative, predictable, and bounded, processes lambda, and then we compute this expectation here. Okay, here we have f of x lambda t, where x lambda t is the counting process associated to lambda at time t, and then we have this let's call it some energy quantity which measures in particular the stochastic intensity. Okay, the thing is that we may consider this functional, this log moment functional as well with the entropy functional. And then we have the quite classical Gibbs variational formula for entropy, which says that actually these two functionals are Legendre conjugates. Okay, that is this functional here is just the Legendre conjugate of this functional, and vice versa, if we take in consideration the following duality given by this. Okay, so this is quite nice. So the thing is that using those two elements, the representation formula for the log moment function and this duality formula, the Gibbs formula, we have that we may have again a variational formula for the entropy, which is quite useful for our purposes. So then we have that this formula takes this form. If we compute the entropy, the relative entropy of a function of a measure mu with respect to the Poisson measure, it has this variational representation. Okay. So the thing is that we are wondering if there are any optimizers for this problem.
Pablo,
Yes.
Sorry, I had a big thunder. Oh, it's a little bit weak. So what is 6t here? Like in the formula, there is no.
The thing is that,
Or-
yeah, I'm sorry, I didn't say it. The thing is that here we are saying that, okay, we are taking the infimum among the class of all these stochastic intensities with which are negative, bounded, and predictable, and such that their counting process at time t has a log. Okay. Yeah, I'm sorry, I quite forgot that. Yeah, this is actually quite important. Yeah, so that's the thing. And then we wonder if there exists an optimizer which attains the infimum. The thing is that this is true. Yes, there is a question.
But where does F enter the formula?
Yeah. The thing is that, first of all, we're supposing that we are given a measure mu, which is absolutely continuous with respect to the Poisson measure, and such that its density, we are taking this role, its density takes this role of F in some sense. Yeah. The thing is that in the following, in the next slide, the function F is gonna play a role, a quite important role. The thing is that actually there is an optimizer. There is a stochastic intensity which attains the infimum, and is the stochastic intensity given by this very particular formula, where we have first of all we define Pt of a function as the Poisson semigroup. This is quite the same as in the Gaussian setting. Okay, so then we have that the optimizer has this really concrete expression. We have the semigroup acting onto the function f. Okay, and we have this structure here. Okay, let's observe actually both the drift and the counting process are coupled in this thing, but actually this is not any problem. Okay. Are there any questions? No. Okay. Awesome. So then the thing is that we call the
Pablo.
Yeah.
Yeah. So that's a kind of a logarithmic gradient, discrete gradient, no? I mean, for the
right. This is actually the exponential of the gradient of the logarithm. Yeah.
Mm-hmm.
Yeah.
Yeah. So it's okay. Yeah. So it's an analogy of the diffusion case for the
Exactly. Yeah. It's almost exactly the same for the Föllmer process, the entropy minimizing for the Gaussian case. Yeah.
Mm-hmm. Okay.
Yeah.
Thank you. Mm-hmm.
So the thing is that we're gonna call the counting process associated to this particular intensity the Poisson-Föllmer process, because of its analogies with the Föllmer process, as Joaquin said, which is the diffusion analog. Okay. So the thing is that in summary, this is a process which has two very important properties. First of all, it is distributed at its endpoint as mu, the measure that we fixed at the very beginning. And on the other hand, it is entropy minimizing. Okay, so we have that for this particular intensity, we have that the entropy of the measure mu with respect to the Poisson measure has this concrete formula here. And we're going to use it a lot. So the thing is that we recall that we have this formula, and for simplicity, we may define this function phi as just the terms that we have here in order to just write the entropy as this. But the nice thing is that actually this function phi is convex, okay, which is something nice. Why? Because first of all, we may prove that the stochastic process lambda t, the stochastic intensity itself, is a martingale. Okay, so this is a first result, which is a consequence actually of the Edo formula for jump processes. That's the proof. And then, of course, if phi is a convex function, then we have that this process here is a submartingale. Okay, so having a submartingale, then we may use some inequalities. So then we're ready to give a proof, a short stochastic proof of Wu's inequality. So what we will do, we will fix a function, a positive function, and we'll suppose that that if we multiply this function with the Poisson distribution, that gives us a probability measure without lots of generality. Okay, so then we may consider the Poisson-Föllmer process associated to this measure mu. Okay, in particular this stochastic intensity lambda. Okay. So then what do we have? We may compute its entropy as using the formula, because of this process was entropy minimizing. Then we may use, of course, Fubini's theorem to exchange the order of integration. And the thing is that we may recall that this is a Stuck martingale, so then we may bound this expectation, but the expectation at the final time. So then we get this thing here. And actually, then if you make the computations, if you use the concrete expression of lambda t, then you may just recover Wu's right-hand side. Okay, so this is the proof. The nice thing is that it is quite short, and the thing is that we use this stochastic process to prove it. Okay. Are there any questions or no? So then let me make an intermezzo in convexity in the discrete setting, because we are going to use it. We recall the notion of what is a convex function on the Euclidean setting, the classical definition. So then if we have that the function f is continuous, then convexity is equivalent actually to this midpoint convexity, which is this property here. Okay. So the thing is that we will take this property here to define what is a convex function in the discrete setting. Okay, so we say that if we take f as a function defined on the natural numbers, then it's going to be convex if and only if it satisfies the midpoint property. Okay, so that's our definition. And the thing is that we may as well define what is a log-concave function. So we say that f, this is in the Euclidean setting, f is log-concave if it is of the form exponential of minus v, where v is a convex potential. Okay. The thing is that log concavity is quite important for the functional inequality context because of the following fact. If we have a measure mu, which is absolutely continuous with respect to the Gaussian measure, and such that its density f with respect to the Gaussian measure is a log concave function, then we have both Poincaré and log-Sobolev inequality. Okay. So we have that if the measure mu is more concave than the Gaussian measure, then we recover nice functional inequalities. Okay. So then the thing is that we may do the same, the very same for the discrete setting. So we may say, okay, what is a discrete log concave function is a function which is of the form f of exponential of minus v, where v is a discrete convex potential. Okay. Then we may say this notion. What is this notion of being more concave than the Poisson measure in this discrete setting? So we say that a measure mu is ultra log concave if it is of this form, if it is absolutely continuous with respect to the Poisson measure, and if its density is just a plain log concave function. Okay. Just some examples to just show that this is a non-empty class of measures. First of all, the Poisson measure satisfies this. As well, we have that the distribution of sums of Bernoulli random variables has this property, and this is a class which is preserved by convolution. So it is a quite rich class. So then we are ready to talk about stability for this inequality. So, sorry, are there any questions up to this point about convexity? No? Cool. Then, what's stability? So, the question of stability, let's recall what was Wu's inequality. It was this thing here. So then for any function, we may define its deficit in terms of this function inequality as just taking the right-hand side and subtracting the left-hand side, which is going to be always non-negative because of Wu's inequality. So then the thing is that this is quite obvious, but if we have that a function f star satisfies attains the equality in Wu, if and only if its deficit is 0. It's quite obvious. So then the thing is, a quite natural question on this context is the following. Suppose that we have a function such that its deficit is quite small, but it's still positive. That is, it's different than 0. Then we are wondering if this function f is close to an optimizer of the inequality. Okay, so that's the stability question. Okay. So the thing is that we were able to prove the following result. So first of all, we fix a parameter t for our Poisson distribution. So then we say take an ultra-log-concave function f, okay, and then normalize it to define this measure here, okay, this measure mu. So then what we have is that we may control, we have a lower bound for the deficit of f, which is an ultra-concave function, by this, which is 1/2 times this function theta cf of this parameter here. We consider this as just a parameter, and we have that this function theta c is defined by this. This is a non-negative function, and which is and it is convex. And the thing is that this parameter cf is the C-log concavity parameter of the coefficient of the function f. So let me explain what is this thing. This parameter cf quantifies the strong log concavity of the function f. According to Johnson, he gave actually this definition of strong or C-log concavity. And in particular, we have that for ultra log concave functions, we may compute it, and it has this very particular form. Cf is just equal to f of 0 divided by f of 1. Okay, so then you may replace this cf for this computation here. Okay. We have that which are the optimizers. As I said before, the optimizers for Wu's inequality are the functions of this form, that is exponential of ak plus b for some constants a and b. The thing is that we have for ultra concave that this deficit is always positive. And the thing is that for equality cases, that is for functions like this, we have that always this strong log concavity coefficient is always 0. You may think about it that, okay, this function here, if we take logarithm, it is at the same, it is an affine function, then it is a convex function, and it is a concave function. So then intuitively, we have that this value here is going to be 0 for these functions. Okay. And on the other hand, why this represents stability result? Because we have that this function, if we take a fixed value of z, we have that if we take the parameter c towards 0, we have that this converges to 0, which is the value for that an optimizer is gonna attain. Okay, so in some sense, this function here tells us how far I am from an optimizer of the quality. Okay, so this is the stability result. Are there any questions? If not, I'll pass towards the last part of the talk. But before, how much time do I have?
Yeah, you have like 15 minutes.
Oh, nice. Perfect. So now what we'll do is to extend Wu's inequality, which holds for the Poisson measure, to actually to a bigger class of measures. So the thing is that recall that in the Gaussian, in the Euclidean setting, we have that being more log-concave than the Gaussian measure allows us to transfer the nice functional inequalities that hold for the Gaussian measure, that is Poisson-Föllmer and log-Sobolev, towards these log-concave perturbations of the Gaussian measure. Okay. So the thing is that in the discrete setting, the ultra-log-concave measures are the ones which satisfy this notion for the discrete setting. Okay, that is an ULC measure is a measure which is more log-concave than the Poisson measure. Okay. So the thing is that we want to transport Wu's inequality towards any of these functions. Okay. And I say transport because I want to do a transport proof, because I love transport. But the thing is that we have lots of abstractions to transport measures in the discrete setting. The thing is that, okay, suppose that we have a nice measure mu. Think about mu. Think of mu about like being the Gaussian measure, and we perturb it and define, and then we define this measure mu. Okay, which is the perturbation of the former measure. So then, if we had a nice map which pushes forward the nice measure towards the perturbed one, if we suppose some regularity for this map, in particular if this map is global elliptic, then we may transport this function inequalities. Actually, this is what I talked to you in January in the summer school. So the thing is that in the Euclidean setting, this is a quite a good useful strategy. Okay. The thing is that in the discrete setting, this is not quite easy. It is not quite easy to obtain some push forwards, first of all. Why? Let's think about a very toy example. Let's think about the 2-point space, that is 0 and 1. So think about mu as being the measure, that the uniform measure, that is, we put 1/2 at 0 and 1/2 at 1, okay? And we have this measure nu, which is gonna be, we're gonna put different weights. In particular, we may put 3/4 on 0 and the rest on 1, okay? So the thing is that I'll give you 5 seconds in order to convince you. You may convince yourselves that actually it's quite impossible to obtain a map such that we have this, okay? It's impossible to obtain a push forward. So the thing is that in the discrete setting, this is not very useful. Sorry, it's not very possible. But even if we had such a nice map, the problem is that the discrete derivatives are not that nice because, for example, we don't have any chain rule for this finite differences operator. So then we cannot apply the chain rule, which is quite useful in this kind of proof that we can do in the Euclidean setting. Okay, so the thing is that we have a little bit of hope, because actually we may work at the Malliavin level to get a transport proof. Why? First of all, let me recall that we, for our metric space E, we have its Poisson space, the canonical space defined. So the thing is that what is Malliavin calculus in general? Because like if a calculus is okay, I take a function which takes just a single value of our Brownian motion of our diffusion process. That is, we fix an instant of time t, and then we may do some calculus about that. The thing is that Malliavin calculus in general tries to do the thing in a wider sense, that okay, I want to take a function which is going to depend on the wall or path of the process. So actually, this is like the morally what we want to do with Malliavin calculus. And the thing is that, as I said, well, here the most important thing is to take to differentiate things. So we may define for a function f defined on the canonical space its Malliavin derivative as the following device. It's just a finite differences operator, but taking in consideration the structure of this space. So actually, we're taking this derivative at the point x is going to be defined as f of the path omega plus this. I am adding this atom x. Okay, this is just a Dirac delta, and then I'm just subtracting f of omega to make the finite difference. Okay. So the thing is that Wu's inequality, what he did to prove the inequality for the Poisson measure on the non-negative integers, on the natural numbers, was to do it at a Malliavin level first. So the thing is that the following is his theorem. So suppose that we have a metric space E, and then we may construct its Poisson space, its canonical Poisson space. So we have that for any function which is L1 and positive defined on the canonical space, what we have is that we may control the entropy of this function big F with respect to the canonical measure P by this term here, which is reminiscent of the former inequality, which holds for the Poisson distribution. Okay, so here we have this integral we're integrating on the space E, okay, which is the metric space with respect to the measure mu. And here we're having actually the very same functional psi, okay, depending on F and the Malliavin derivative of F at the point X, okay? So the thing is that what I claim is that the Poisson-Föllmer can be regarded as a transport map. Why? Suppose that we have a measure mu, which is absolutely continuous with respect to the Poisson measure, and suppose that it has a log-concave density, okay, always in the discrete sense. Then we may consider X lambda as the Poisson-Föllmer process associated to this measure mu, which was the entropy minimizing process, okay? And the thing is that we recall that at time t, big T, this process was distributed as mu, okay? So then by definition of what is the law of a process, we have that the measure mu is a push forward. In particular, it is the push forward of the measure of the canonical measure P by the map xt lambda, okay, which is quite nice. So the thing is that the theorem that we were able to prove is the following. So first of all, we fix a parameter t for the Poisson distribution, and we're going to suppose that we have a measure mu, which is absolutely continuous with respect to this Poisson distribution, and which has a log-concave density f, okay? So then what we have is that this measure mu satisfies the Wu's inequality. That is, for it, there exists a constant which is going to depend on the particular measure that we are looking at. Such that for it positive function, we have Wu's inequality, but instead of t here, we have this different constant, okay? And this is just the very same energy term, okay? So first, some remarks about this constant here. We have that our constant is sharp, because for the Poisson measure, this is just t, that is the Wu constant, okay? And actually, it is the best known constant for this kind of inequality for ultra-log-concave measures. Because formerly we had this approach by Johnson, by looking this C strong log concavity, and where he used that definition in order to do some Bacri-Méry techniques in order to prove this modified log-Sobolev inequality. The thing is that we can do better actually by this method, okay? So the thing is that the proof it's not that long. We have, first of all, we're gonna take up a non-negative function g, and we're gonna compute its entropy with respect to the measure mu. Okay. So then we use the fact that we have this map push forwarding the canonical measure towards mu to write this entropy as this. This is just the change of variables. Okay. So then what can we do? Because here we're doing actually things at the level of the canonical space, because we have the canonical measure P. Then we may use Wu's inequality at the Poisson space to get this inequality here, okay? The thing is that here we have some term, and here we have this Malliavin derivative, which we wanna handle, we wanna control. The thing is that this lemma, the following lemma, is a big consequence of the log concavity hypothesis that are in play. Okay, so actually under this hypothesis, we may prove that the Malliavin derivative of this process of xt lambda is always 0 or 1 almost surely. Okay, And in particular, as a consequence of that fact, we have that we have the following chain rule, which is the following, okay? Which is quite useful. So then what we can do, we can actually apply this chain rule to compute this term here, okay? So then we do that and we get this equation here. And the thing is that then if we observe this term more carefully, we have that this thing here is always 0 or 1. And for example, if it is 0, actually we may you can do the computation and you get that if this all this thing is 0, then the function psi is 0. And if this is equal to 1, then it's just all of this is just equal to this. So then we have at the end this equality here. Okay, so this is useful because we may apply it to this term here to get the next one. This is nice because first of all we may pull out this term here from the integral because it does not depend on z and small t. Okay, so then we're just left with this term here with this integral that we want to control, and actually over there we just we use some things given by the log-concavity hypothesis to get the constant, okay, to get a pointwise bound for this term, and that's how we get our constant CB. And then the thing is that, okay, we have this thing here, but we are still at the Malliavin level. So then what can we do to get, because here we would like to get just expectation with respect to mu, okay? We just have to undo the push forward, okay? And then we get what we want. And the thing is that actually this technique could be used as well for more inequalities. We may extend as well the satisfies size entropies. So then Wu, Poincaré, and some other inequalities are particular cases. We may transport as well the Martin and Talleyrand T1 transport inequality, and as well we may transport FKG inequality. So thank you so much. That's all.
Okay, thanks, Pablo, for your nice talk. Are there any questions? Or any other questions? Joaquin, maybe? Let's start
Yes, I see there is Abelio too. Maybe I start or as you want. Or Abelio, as you prefer.
No. So if you take more than 5 minutes, I will cut you in.
Okay. No, probably not. I hope so. Pablo, yeah. Okay. Yes. Very nice approach, I think, to the question, and I would have expected to see some stochastic process that has the Poisson distribution as the invariant distribution somewhere, because that's what you do. I mean, if you want to prove log-Sobolev inequality, at some point you will deal with some Ornstein-Uhlenbeck process.
Mm-hmm.
But here I wonder if it's kind of hidden because I got
totally your question. The thing is that what you're talking about, like if we want to prove log-Sobolev for the Gaussian measure, then we take Ornstein-Uhlenbeck, which is a process which is defined at every instant of time, and then we have that. In some sense, we have the ergodic measure is the Gaussian measure, and then we use these Bacri-Méry techniques and everything that we want. The thing is that here, what you are doing, the nice thing about these Föllmer-like processes is that they are condensed into this compact time interval. They are condensed onto 0 and t. Okay, so then it's in some sense equivalent to say that okay, at the final time I'm distributing the measure that I want. It's the same as saying, okay, I just wanna, if I take a Langevin process, then I want to be ergodic with that distribution. Okay, so that's actually I think for example in the Euclidean case there are some conversion formulas. For example, you may pass from the Ortan-Uhlenbeck towards Föllmer, if I am not wrong. I'm not pretty sure, but I think you can rescale time in some sense and get the same elements. Yeah.
Okay. Yeah, I see more or less. Yeah, so in order to keep my question bounded, I will probably ask you later through other channels. Okay, continue the discussion.
Yeah. Whenever you want to.
Thank you. Nice talk
Welcome.
and results.
Pablo, do you want to ask something?
Yes, so thank you, Pablo, for the talk. So my doubt was the FKG. Can you tell me a little bit more of what do you mean, what you apply it in FKG?
Oh yeah, sure. Let me write a little bit. Let me add. Okay. So the thing is that what is FKG's inequality? So we have that in the discrete setting we have that measure. Sorry, a measure satisfies FKG. Sorry, if and only if we have that. For each function f and g such that their gradients, the discrete gradients, are not negative, then we have that we may have a bound for their covariance. That is, we have that expectation of f minus expectation of f times g minus exponential expectation of g. This is always non-negative. Okay, so that's FKG inequality. And the thing is that what we it's a classical theorem that FKG holds for the Poisson measure. Okay, so then actually what you can do is just the thing is that FKG is satisfied at the Malliavin level. Okay, so then what you can do is just use the same transport map in order to transport FKG inequality in this form here towards your ultra log-concave measure.
Yeah, but what I'm lost here is like if you have just a one-dimensional thing, you always have FKG. It's not only for
if you have one-dimensional.
So FKG makes sense. I mean, it's more interesting when you have like a percolation because you have a. I mean, it's not one, but if in one dimension, I think it's just in general, like because the proof just essentially works. I mean, if you want it, every measure is just a increasing thing of 0, 1. So you are putting things on top of it.
I see.
I believe maybe.
Don't you need some symmetry, Aurelio? I mean, I'm thinking in the case of uniform in 0, 1, and when you do the proof, you can replace u by 1 minus u and independent.
I mean, if it works for functions of uniform, then you are good, no? Because everything is a monotone function of a uniform random variable. So you just need to show FKG for uniform ones. So maybe we can see it afterwards. It is too late in Europe, so I may. Thank you.
Okay, any other questions?
But yeah, you have the symmetry, I think. Maybe. Okay. No, I don't have.
Okay, so if there are no other questions, we thank Pablo again.
Thank you so much. It was a pleasure.